we are going to the theory of buckling under centric loading. So yesterday we drew a structure that is very long in length relative to the cross-sectional area is very small. So this structure you see over here, on one end you have built-in, and the other hand is so-called free for now, but you have applied load P acting on the neutral axis, sorry, at the centroid. Okay. So the next thing that we are going to look at, before I go on, what we are trying to achieve at the end of the day is we are trying to prove, I'll move this down here. We are going to derive, we're going to derive that the stress critical is equal to pi squared EI over L squared A. This is the first time in any structure analysis formula they have seen that we have a what? We have the term what? Pi squared. Okay. How is it possible we get a pi squared in a structure analysis question or configuration? The next diagram I'm going to draw on the right hand side now, okay, we have two axes. So this is one of the axes. Okay. So this is, I'm going to label this as our y-axis. And another axis that we're going to have this will be our x-axis. And I'm going to sketch how the structure, the deformation pattern due to buckling now. Okay, so this is a sketch. Okay. And we're going to impose two boundary conditions. We're going to impose two boundary conditions. Now, the deformation is that way. Let me explain. Let me explain what we are trying. Why is it like this? Okay. In real life, in buckling, right? In reality, in buckling, what is going to happen is, if I want you to focus on my finger, like my left finger over here. When buckling occurs, so what is happening is I hold this tight. This is a slender structure, i.e. the thickness over here is very narrow. So when I push it down, can you see how the structure will be formed? Yes or no? Right? Over here, we are going to assume that the load will not move left or right. It will just come down vertically. Are we clear? It will just come down vertically. Now, one thing I want you to also take note. This is the cross-sectional area that you, or the face you see now. And you see buckling occur about this curvature, yes or no? If I turn the structure around and I try to press it down, can you all see the buckling occur when you look at my ruler? Can you look at the deformation? How does the deformation look like? Does it look like buckling, yes or no? No. I repeat again. If you look at my ruler now, okay, on this face, okay, at this orientation now. When I press the ruler down, at the side, it looks like buckling. Agree or not? Disagree? Yes. But from the front, does it look like buckling? No. Okay. I want you to take note of this because later on, we are going to determine which axis buckling occurs. Do not memorize all this. All this, what you need is a long ruler. Are we clear? Okay, all you need is a long ruler. Now, as I mentioned earlier, we are going to assume what? The load P is moving about the vertical axis only. Okay, so the P motion is about the vertical axis. So P will always move along the what? This is our centroid. So P, I'll put down here, P will move along the centroid axis only. It will not go left, neither will it go right. So the first thing that we're going to define now is our boundary condition number 1. So boundary condition number 1 states where this is x equal to 0, y is also equal to what? 0. Then we're going to impose boundary condition number 2. When x is equal to 0, sorry, x is equal, now when I put over here, this is approximately equal to L0, y is equal to 0. What you see over here is our deformation pattern. Okay. And basically, we need a mathematical description on how the structure is deforming. Daniel, where are you? Where's Daniel? Daniel, where are you? I need your critical mind now. Why y is approximately equal to L0? Why L is not equal to L? Don't be afraid. I know you know the answer. Yes. Yes, well done. There is a change in what? Length. Okay, there's a change in length. Okay. What we are trying to predict is the onset before buckling occurs. Okay, so we are trying to predict at this moment. Okay, we are not trying to predict this. Okay, we are trying to predict when it will what? Initiate. When it initiate, it will already what? Correct. Okay. How many of you drink Coca-Cola? How many of you have a can Coca-Cola that's empty now? Okay, I want you to try this. Stand on your Coca-Cola, and while standing on it, I'm too old to do that now. Okay, if I do that now, probably the cost will be taught by someone else. And then you press the center of the can of the Coca-Cola, all of a sudden it will what? Correct. Yes or no? We are trying to predict the onset before when you just touch the side of can of the Coca-Cola can lightly when the whole thing works. Correct. Okay. Something smells good from the sorry. I was going to like have a spoon face, I think. It's okay. I do apologize. Do not embarrass you like that. Okay, no mocking around. So we are going to pick a point down here, an arbitrary point. And this point we're going to pick is known as what? Q. Okay. And at this point, we are aware that we have a distance from here to here. We have a specific distance over here. So this is our y. And then there's another specific distance. Over here now. And over here, this is our x. Okay. So x is basically telling us along the beam at a specific distance, what is y? Y over here, it represents our deflection. Okay. So now we are going to sketch the free body diagram. Okay, we're going to sketch the free body diagram at point Q, or between x is equal to 0 to point Q. Okay, we're going to sketch that now. So when we sketch that, how does it look like? Okay, so now this dot over here is where what we have is x is equal to 0. And then at a certain distance over here, this is our point Q. Okay. So we know when x is equal to 0, we have a load coming down as P. I'm going to now sketch a line representing the centroid. Okay, this is our centroid now. So when this is the case, we are going to apply static analysis. Okay, we're going to apply the static analysis. So we are aware that there is a counter what? A counter force over here. And I'm going to call this P. Agree? Right? Because we are carrying on what? Static analysis. So point Q and point A is no motion. Okay? Then we realize that the load applied at point Q have a certain distance over here. And the distance from here to here, hold on. This distance from here to here is known as what? Y. Okay. So relative to the what? Relative to the centroid, right? There will be a moment acting in this direction. Or at point naught, there's a moment acting in this direction. And let me change the color, I do apologize. There is a moment acting in this direction. Okay. So if why there's a moment acting in that direction? Because at point Q, we have a moment acting in this direction. Because P is offset by a certain what? By a certain distance Y, and there is a moment acting at point Q, and where we have x equal to 0, you have a counter moment. If you don't have a counter moment, what will happen is the structure will start to what? Rotate. Hold on. Our structure will start to what? Rotate. Are we clear? So that has to have a counter moment, then the bending or the buckling will be on the centroid. Yes. Is this direction, because the centroid is the fixed point. So you have a perpendicular distance over here, so it's acting the moment this way. Okay. Now, from here, we know that MQ is equal to, wait, let me rephrase that. I don't think I explained that. Wait, sorry, I retract that. What we see now, okay, we are concerned with what is going on. Okay, we are going to focus at point Q. So point Q is our reference point, yes or no? So